So today I'm going to show you how to store data on an Arduino in non-volatile memory, so that if you switch the Arduino off, it loses power, and you turn it back on, you can still access that data. We're going to be using something called electrically erasable programmable read-only memory, or EEPROM, which has 8-bit or 1 byte storage per address, and 1K or 1024 bytes in total. So let's have a look at the code now for how to use the EEPROM. We're going to just store some basic configuration information. I'm not going to show you the CLI, the command line kind of text interface. I've shown that in a different video, but basically I'm able to input config values, and now what I want is different to what I had previously, which is I'd need to change the config values if I wanted them to differ from the defaults every time that I ran this sketch on the Arduino. Now I want it to actually store it somewhere, so that even if it loses power and it comes back on, it's not lost. It's not stored in volatile memory, it's stored in non-volatile memory, in this case the EEPROM, which is the electronically erasable programmable read-only memory. That's what it stands for. So there's a library for this stuff called EEPROM, and we'll have a look at it in a sec. So what I'm doing in my setup method is I am saying that I want to load all the config, and that's going to actually pull it from EEPROM if it's there, and load it in. So let's have a look at that method. Okay, so in my case I have 3 different configurations: one about sending data to Sigfox being enabled, a sample size, and a delay. Now I've called this internal method that I wrote for each one. In this one is a boolean, so I've written a load bool config, because it's a bit different to load int config. So I've got some booleans and some ints, and we'll see why that differs in a moment. So if we have a look at those different methods, let's have a look at load bool config first, and save bool, so these two. So when we're saving, it's very simple. Somewhere else in here, when I actually set the config, I just call save bool config, and I pass through the config value, which is a boolean, and the start address. I've got constants that I've defined for these various start addresses. Like for the Sigfox one, it's a 0. I save it into address 0, but you can choose whatever you want. The address, however, must, because you have 1K of EEPROM on an Arduino Uno at least, the address needs to be between 0 and 1023. So that's the restriction on that. Then you use the EEPROM library, and to save it or to write it to the EEPROM, you just call EEPROM.write. You specify the address and you pass it through a byte that you wanna save. So now with the bool config, that's easy because a bool is like 1 bit. So a particular address here could have a byte, which is 8 bits. So that's big enough to fit the data that you want to store. So there's no problem there. Then loading the bool config is also really easy. You just use the EEPROM's read method, and again you specify the start address. So if the start address you wrote to and the one you read from is the same, you get the same value. Now I've specifically just said if the byte read is 255, then I return a default value, which is the default value for this particular configuration, and that's just because that's what it returns if I haven't actually written anything there explicitly yet. And if it's anything else, then I just return, in this case, I cast it to a bool. I cast the byte that I read to a bool because I know I'm loading a bool config. Okay, so that's it for booleans. It's quite easy. Where it gets a bit more complex is for the other ones that I wanted to do, which were ints, right? So let's just have a look at loading int config and saving int config. Okay, so this is where things get a bit trickier. Now the reason they get trickier is because the ints are 16-bit. So you need 2 bytes potentially to store the int value that you're specifying. Okay. Now with the EEPROM libraries functions like write, it's not like you're specifying a start address. Actually, you're specifying a specific address, and you got to give it a byte, and it'll just put that byte in there. If you give it something that has more than 1 byte's worth of data, it effectively ignores the higher bit, so it would just drop the higher bit. It's the same as if they were all zeros. So you actually need to split this into 2 bits is the way to think about it, and that's why I you see I have the byte to store, I set it to a certain value, and I write it to start address. Then I do something on it, and I'll explain that in a moment, and then I write it to start address +1. I write the new value. So then we have two consecutive bytes in the EEPROM that together store this int value that we wanted. Okay, so what do we do here? So the first thing we're doing to get the lower byte, and I'll show this in a little picture what it's doing exactly in a moment. But basically what we're doing is we are applying a mask. So this 0xFF is effectively a mask. If you think of 16 bits, the first 8, so if you go from right to left, because all this stuff's like a little Indian ordering. So if you go from right to left, it's the first 8 are 1s, and then the next 8 are 0s. And when you apply that mask to the config value, as I'll show you shortly, basically what it does is it kind of chops off the higher byte, and you're left with the correct values for the lower byte. And then, so this is where we're actually writing the lower byte to the EEPROM. Then what we do is we take the original value and we do a 8-bit shift to the right. So that takes the higher byte, the higher 8 bits, and it shifts them and basically overwrites the lower 8 bits with whatever the higher 8 bits were or are, and then it just slots in like 8 zeros on the left now where sort of space is opened up. And that's how we get the higher byte, and then we write that now to start address +1. Okay, so that's how we do the saving of the int config. Now loading of the int config is like kind of the reverse of the saving. So what I've done here is I've read the lower byte from start address, I've read the higher byte from start address +1, and then again I've just checked if they both set to my EEPROM default value, which is 255. I actually see over here I hard coded it in the boolean one. Yeah, they should actually just use my constants. That's set to 255. Then we return the default value that was passed through. That's the default value for the config. So let's not worry about that piece for now. Let's look at the else. Okay. So what we then do is we take the higher byte and we bit shift it by 8 now to the left. So the opposite of what we did previously. Okay, so this is just undoing like what we did originally. So that gives us the original higher byte as an int. Okay, so it's very important that you store it as an int. If you stored it as a byte, it would just give you 0 because you'd be chopping off the higher 8 bits anyway. And then again, we also store the original full value as an int. And the way we just get that is we just take the original higher byte as an int, which is this bit shifted value over here, and we add it to the lower byte that's been cast to an int, and then you return the original value. So if on save int config we pass through like 1, 2, 3, 4 as the value, it would split it apart, save it in 2 different addresses. Then when you said load from that same start address, what it would give you as this original full value would be the same, whatever I said it was, 1, 2, 3, 4, or whatever. So if you pass through 1, 2, 3, 4 as a config value, yeah, you'd get 1, 2, 3, 4 out as the original full value there. So that's the code for it, and let's have a look at how it works quickly. So I'm going to just run this quickly on my Arduino. It's already plugged in. Have a look at the serial monitor, because I've got a little text-based like command line sort of interface here. So if I say show config, it's going to show me my current configuration settings. Okay, so all of these things. I'm just going to change one of them. So I'm going to change my delay from 200 milliseconds to 2 seconds. So 2000, let's call it 2001, make it a little different. Okay, now if I show config, you can see that it's changed to 2001. Okay, so now I'm going to close this. I'm actually unplugging my Arduino, so it's lost power. I'm going to plug it back in. Right, I can even re-upload the sketch at this point if I want to. It's not really necessary. If I go back to the serial monitor and I say show config, just give it a moment. There we go. Okay, It just took a while because I'd up the delay and I has to wait for the delay before it goes to the next loop. So now you can see the delay is 2001, which was different to the original defaults, which was 200. Yeah, so if I actually reset config, then you'll see that it will change back to like the factory defaults, which is back to 200. So it was at 2001. So that was even after I pulled the Arduino out, it lost power, all volatile memory would have been cleared, put it back in. You see it kept that. So that's basically how you do it. And yeah, that will allow you to persist data. As I said, it's only 1K with the data, but it's quite useful to know how to do. So let's have a look at an example of how this masking and all that stuff works, the stuff I implemented in the code I just showed you. So if we've got 1234 as the int we want to store, it's stored across two addresses, address 0 and address 1, each of which are 8 bits because it's 16 bits in total. If this is effectively how it needs to be stored at the end of the day, if we're doing a little endian, the lower byte would be in address 0 and the higher byte in address 1. You can see the binary representations. Concatenated together, lower and higher on the left and lower on the right. That's what it looks like. If you then mask it with a mask that just has ones for the lower end, the lower 8 bits, this is the result you get. It effectively zeroes out the higher byte, and then we store that in address 0. Then in address 1 we want to store the higher byte, so we take that and we do an 8-bit shift, which gives you this result that I'm showing you now. It's all zeros that will replace the stuff that shifted across, and that's it really. That's how you split it into two and store it. So that's a simple example, and I've already showed you the code implementation. Hope you found this useful, and please subscribe to my channel for more videos.